Hello, chemistry students. So in this particular video, we're going to talk about the photoelectric effect and how it helps us use a formula to calculate energy in light. So it was discovered that when light strikes metals, electrons can be ejected. We'll call this uh, electron ejection. It requires a certain amount of work. It's known as a work function psi. And we'll call that the ionization energy. It's the amount of energy required to remove an electron from a metal surface. So when electromagnetic radiation above a certain frequency is shined, we can see that an electrical current registers on a meter. And that electrical current is a form of energy. So as frequency increases, the current increases. But below a certain cutoff frequency, no current is obtained. What that means is within this device, electrons are not being ejected and they are not being registered in their voltage meter, and that's because they're not at the correct frequency, which is referred to as the threshold frequency. So amplitude, it doesn't matter how intense the light is or how bright or dim, amplitude does not affect the ejection of the electrons. It has to be at a certain frequency. And remember, as frequency increases, wavelength decreases. As frequency increases, energy, we're going to see increases as well. So Einstein proposed that light seen in the photoelectric effect is given off in forms of packets, and we're going to call that quanta or photons. Unlike classical theory that viewed light as a wave whose intensity is variable, Einstein suggested light was actually lumpy, and those are those quanta or packets of photons. From this perspective, light is not a wave, but it's a shower of particles. And each particle, each photon, has a certain amount of energy, and it's Planck's times frequency of light. So the energy of the photon of light is directly proportional to its frequency. So using Planck's constant of 6.626 times 10 to the negative 34 joules seconds, we get two equations. We get, again, energy is directly proportional to frequency. As frequency increases, so does energy. We saw that ultraviolet light has a higher frequency, a shorter wavelength, and has more energy. Now, earlier we've seen in videos that the speed of light is equal to wavelength times frequency. If I solve for frequency, I see that frequency is equal to the speed of light divided by wavelength. And I can now substitute this quotient for frequency. And that's what I have right here. And it also makes sense as wavelength goes up, energy is going to decrease. Okay? Because it's in the denominator. So what is the wavelength of a particle or a packet, a photon, that has energy of 4.41 times 10 to the negative 19 joules? It's not a lot of energy, but we're just talking about one photon of light. So we're going to need two equations and two constants. One, the speed of light equals wavelength times frequency, and two, energy is equal to Planck's constant times frequency. And the two constants, the speed of light and Planck's constant. We can then substitute for frequency, as I said earlier, by rearranging this equation, speed of light divided by lambda, and we get this new equation. Now, if I want to solve for wavelength, I can directly plug into this equation and then solve for wavelength, or algebraically manipulate it and rearrange it. So what I see is wavelength equals Planck's constant times the speed of light constant divided by the energy of the photon. So I plug in my constants and I divide by the energy of the photon. What I also see is the joule seconds, the seconds cancel, I see the joules cancel, and I'm left in wavelength in terms of meters. So the wavelength would be 4.50 times 10 to the negative 7 meters. If I had a multiple choice problem like this, it'd be easier to kind of just see that that is 450 nanometers. If the problem asks for you to give wavelength in nanometers, we could easily do that because we remember that in 1 meter, there's a billion nanometers, and we end up getting 4.50 times 10 to the squared nanometers. What if I actually have to calculate the energy of not one photon, but a mole of photons of, I don't know, let's say red light? Well, they'd either have to give you the wavelength of the red light, or they'd have to give you the frequency. Either way, it doesn't really matter. If they gave you wavelength, you could determine the frequency because we know the speed of light is lambda times frequency. We could plug in the lambda here, plug in our speed of light. Of course, you would have to change nanometers into meters. And again, you could easily do that. That's because you know that in 1 meter, there's 10 to the 9 nanometers. So this would be 699 times 10 to the negative 9 meters, or you could just leave it at that and plug it in, and you would be able to solve for frequency. So if you have that, if you have frequency already, you could plug it directly into this photoelectric effect, this equation that was derived from Einstein using Planck's constant, or if you have lambda, to get frequency using the speed of light. So once we have it, we plug it in, we plug in Planck's constant, we plug in the frequency, and really this value of 2.85 times 10 to the 19 joules is per photon, right? And notice it's a 10 to the negative 19, similar to that last problem. But this problem wants to know in a mole of photons, right? So how do I do that? I use conversion factors. This is joules per photon. I know that there's 6.022 times 10 to the 23rd photons in 1 mole of photon. So I end up getting this number. And now this is a number that seems like it makes more sense to us. The reason why it makes more sense, it's not this tiny negative number, but realize only 1 photon would be a small amount. And light showers you with photons, and because there's so many photons, it makes more sense to do it in terms of moles. So this number makes numerically more sense. Now, that's kind of a lot of joules, so what would be a good thing to turn this into? Instead of joules per mole, we can convert it to kilojoules per mole. And how would we do that? We would just take this number, and we know there's 1,000 joules per 1 kilojoule, or we can just take this and move it over 1, 2, 3, and we would round up. So there's 172 kilojoules per mole of energy in 1 mole of red light. And again, that's enough energy to actually break some weak bonds. And we'll be learning that later with bond energies in chapter 8 and 9. So thanks for watching. And if you have any questions, go ahead and leave me an email.